Hello all, welcome to part 19 of the Wireless LAN Security Mega Primer. In this video, we will look at the fragmentation and Hirte attack. So the first thing is to understand a little bit more about fragmentation. The basic idea behind fragmentation is that you may have a very large frame which you want to transmit over wireless, and this frame is much larger than the maximum transferable unit for the given network, and hence we need to break this frame up into multiple packets, each of which are called fragments of that packet. So you have fragment 0, fragment 1, fragment 2 and fragment 3, where the whole idea is to take the data of the original packet and actually create an absolutely new packet containing it. So what are the different header fields, if you recall, I think in chapter 2 or 3 which we talked about, which help in this? Well, this is where the sequence control header field comes in, which is further divided into the fragment number and the sequence number. Now, for any given large packet which we are breaking up, the sequence number is constant. The only thing which changes is the fragment number. So as an example, let's say when we break up this packet, the sequence number may be set to 1, 2, 3, and the fragment numbers would vary from 0, 1, 2 and 3, assuming we are breaking it up into 4 different fragments. Now there is also one other bit which is, if you remember, part of the frame control field, and that is called more fragments. So how does this help? Well, apart from the last fragment, which is fragment 3, all other fragments, right, from 0, 1 and 2 will actually have more fragments bit set to 1. So this basically indicates that more fragments are yet to arrive, so the receiver will wait and not reassemble the packet. So now, what is the fragmentation attack? So before we go into that, we will analyze a little bit of the packet which goes over the air. Now I have actually captured a little ARP packet, and this is how an encrypted ARP packet would look like, or for that matter, even a plain text ARP packet. One of the important things is after the 802.11 header, you actually have the logical link control header, right? The LLC. And this is 8 bytes in totality, consisting of a lot of small fields here. And the funny thing is that most of these fields are actually constant, apart from the type, which may vary based on whether it is ARP or IP or some other protocol, right? Now we are going to use this to our advantage in fragmentation attacks. How? Well, this is how. Now, what was noticed is that the LLC header is actually something which is known. These values are known and are predictable. That is, the first byte is AA, then you have another AA, 0300, so on and so forth. Only the last byte, which is part of ether type, is the one which varies. Now you can compare this diagram with the screenshot here, and you will notice we have AAAA0300 followed by 3 zeros, then 08 and 06. And this is exactly what it is. 06 would be for ARP. Now, what is the observation? The observation is the LLC header is known. Size of the LLC header is 8 bytes. Now, the only thing unknown was the last byte based on the ether type, and that could be ARP or typically IP. Now, is it possible to decipher that as well? Now, interestingly, the size of the packet indicates whether it can be an ARP or an IP packet. And this is how, just by looking at the packet size, even this last byte can be guessed. Now, this brings us to a very interesting conclusion that even if a packet is encrypted, we actually know the first 8 bytes, which is the LLC header. So if I were to break up our original packet, basically you had the data and the ICV, both of which were encrypted, if you remember, and the data is the encrypted data and the encrypted ICV after XORing with the key stream happens, right? Now our observation is that the first 8 bytes of the data consists of the LLC header, and we know each and every value in those 8 bytes in a predictable way regardless of the packet. Now what this brings us to is something called the known plain text attack in cryptography. So what is a known plain text attack? Well, there is an encrypted packet, but we actually know part or whole of the plain text which is present in the packet before encryption. So now all we have to do to get the key stream is take the plain text LLC header, which we know basically from this diagram if you remember, each and every byte, and we just XOR it with the encrypted data in the packet. When that happens, the output is actually the RC4 key stream. The first 8 bytes, please remember. So by this technique, we can predictably and reliably get the first 8 bytes of the RC4 key stream of any packet which is over the air. This is very powerful. Now, what can we do with this? So what do we have now? We have the RC4 key stream, that is 8 bytes of it, and of course the corresponding IV, which is always available in plain text as part of the WLAN header along with this. Now what we can do is think about it. We could actually create a very small packet of 8 bytes where the data is 4 bytes, and we calculate the ICV for this data, which will of course have to be 4 bytes because that is a requirement. Now we can take the RC4 key stream which we just got because we were able to guess the LLC header, and then we can XOR both of these to actually get an encrypted data and the corresponding encrypted ICV, right? Now the beauty is this packet along with the IV which was captured previously is a absolutely perfectly valid web packet for that network. This means if we transmit this packet, send it to an access point or a client which is part of that web network, it will happily accept the packet, right? But you must be wondering, well, what can we do with just 4 bytes? I mean, nothing is going to fit in there. This is where fragmentation comes to our rescue. So let's say you have a large chunk of data which you want to send over the web network, but you are unaware of the web key, and all you were able to do till now is figure out 8 bytes of key stream based on the known plain text attack with the LLC header. Now what you need to do is you need to break up your large packet into 4 byte chunks and then go ahead and create these small 4 byte packets with the 4 byte ICV for each of these chunks. Now the point to note is the maximum number of fragments possible is 16, which actually means that if each packet is 4 bytes, then you can transmit a maximum packet size of 64 bytes, which if you think about it is quite enough to do a lot of ARP-based replay attacks and even some IP-based attacks. Of course, you can try and weave in other higher layer fragmentation along with this to actually transmit even much larger IP and TCP attacks packets, right? So quick summarization. Fragmentation attack, what is it all about? Well, observation 1, we know the LLC header. Observation 2, it is always in the first 8 bytes of a packet. Observation 3, because RC4 is a simple XOR, we can take that known plain text LLC header, XOR it with any encrypted packet we see over the air, and get 8 bytes of RC4 key stream and the corresponding initialization vector. Now using this, we can create any 8 byte data packet which is valid for that web network even without knowing the web key. Now when we have 8 bytes, we will always have to dedicate 4 bytes to the ICV and 4 bytes to the actual data, which means for any given fragmented packet which we will create, we can at most push in 4 bytes of actual data. What this would actually mean is for a very large data, we would have to break it up into 4-byte segments and then transmit each of these in a packet. The only limitation of fragmentation is we can transmit at most 16 fragments for any given packet, which brings the maximum amount of data which we can send to 64 bytes. So now, what is the Hirte attack? Well, Hirte attack uses the concepts of both the cafe latte as well as the fragmentation attack. Basically, this also works on any client which is isolated. So what it does is, just like in the cafe latte attack, it will sniff the air, figure out what clients are probing for, and then set up a web API so a client would connect to it. Once that happens, it will probably wait for the auto configuration IP address to be handed over so that the client sends an ARP packet. Then the Hirte attack code will take that ARP packet and basically convert it into an ARP request for the same client. How will it do that? Well, it goes ahead and relocates the client IP address in the packet to make it an ARP request packet for the same client. This is accomplished using fragmentation, where it actually creates two fragments which, when reassembled, create the ARP request packet, right? Now it sends this back to the client, which of course replies because it's an ARP request to its own IP address. And once you start doing this over and over again, sending thousands of these packets, what you basically have is game over, right? You use AeroDump to collect those packets and AirCrackNG to decrypt the web key. Crack the web key, right? So I guess a lot of theory. Now let's go to demo time. So let's actually go ahead and start sniffing for data packets, right? And our friendly Apple client has once again nominated himself to be our victim. And what we are going to do is, for the Hirte attack, well, we have multiple options, but we will use air replay ng to go ahead and do the Hirte attack. Now, as far as air replay is concerned, the --c frag is actually the Hirte attack. So we could actually go ahead and give this as the option, and post that we will also need to set up an SSID, right? The other option, which is one of these, the other one is actually to go ahead and use airbase ng, right, which will set up the access point and all of that. So I'll do it with airbase ng. With air replay ng, you can try it out later. I've already set this up very simply for you. -c1 is basically to run the access point on channel 1. PwnMe is our web-based SSID. -w1 sets the encryption bit in the frames which are being sent out, and mon0 is the interface, and -n is actually for the Hirte attack. Okay. Now what we are also going to do is set up AeroDump on the same channel, and let's do the following. Let's actually write it to a file called Hirte. Right, so AeroDump -ng has been set up, and now what we're going to do is actually set up our access point. Right, so we are able to see the PwnMe access point here, pretty good. And now we will start our client, which will automatically, hopefully, associate to the PwnMe access point, right? So I just started my client, and if you notice, it has automatically connected to the PwnMe network. And I guess basically currently the Airbase NG tool is actually waiting for the ARP packet, right? And we can see the number of data packets is comparatively quite less, but now all of a sudden it's surging ahead, right? Which actually means, well, Airbase NG found the ARP packet and is now going ahead and pumping uh, and using the fragmentation attack ARP requests for the same client, and the client is responding. See, the beauty is actually there is no other access point or anything there, right? And the client is generating data packets for the web key which is cached in it for the PwnMe network, right? You can see from time to time, the arrow dump ng screen output just freezes. As I warned you, this is because of the problem that we are actually running it over VMware. Actually, everything is slowing down. Hopefully it's not going to crash, but anyway, you've kind of understood what is happening in the Heritage attack. Just wanted to show you a little bit about what the data might look like. Let me quickly stop the sniffing. Even this is taking up a lot of cycles. Right, so interestingly, if you notice, we have already entered the web key in Wireshark. That is the reason why you were able to see some of those earlier packets. But now if you notice, this is the traffic created by Airbase NG, right, which is actually sending out these fragmented packets. So it's sending out basically two sets of packets. Let's open up the header to understand this better. If you notice, this actually says, well, this is fragment number 0, sequence number 1293. And the next packet actually goes ahead and says it's fragment number 1, sequence number 1293, right? Now, one of the other important things to note here is that in the frame control field, if we go under flags, if we just look at the first packet in the pair, this will actually say, scroll down here, that more fragments are to come as expected, right? Because this is the first packet. But when we go to the second one, it actually says this is the last fragment, which means we are using two packets to reassemble an ARP request for the client, right? This is how the Heritage attack is working behind the scenes. So let me quit Wireshark, free up some memory here and there. Meantime, let's go back here and see what is happening. One of the problems really is the iPhone kind of goes ahead and switches off the Wi-Fi by itself. So that's the reason why you're currently seeing the data packets have stopped. But it should momentarily kind of reassociate, and then you should very soon actually see the data packets increasing once again, right? Now the tool once again is waiting for start the Heritage attack. Now it actually says, well, it started, and you once again see the packet send-off is jumping forward, right? It's a good idea, as always, to go ahead and start your AirCrack NG so that we can do this. So what I've done is I've kind of put it on power. So when it's on power, the Wi-Fi remains on. I don't have to worry about it just switching off by itself. So we'll use AirCrack NG now, and what we are really interested in is the heritage.cap file, which is getting formed here right now, and let's see what happens. Right, so AirCrack is also running parallelly, and we already have around 12,000 packets, and we are done. Of course, this was a very simple 40-bit web key, but nevertheless, the point remains that we were able to crack the web key with just the client, right? This is exactly the same as what you would do in Cafe Latte. And just to take a little bit of credit, the Cafe Latte was the first attack which actually went ahead and targeted an isolated client. Right, okay, so let's go back to our little slide. Now, hopefully, you understood the concept behind fragmentation attacks and how the Hirte attack uses both uh, concepts of the cafe latte as well as fragmentation. Now, for more details, you can go ahead and study this beautiful paper called The Final Nail in Webb's Coffin. And this talks about a lot more details about what you can do with plain text attacks, with fragmentation and other things. If you're more interested about the actual implementation of the Hirte attack, etc., I guess Aircrack NG website is the best source for you, right? So, quick acknowledgement, a couple of those images, especially with the figure IDs, were taken from this paper. Just wanted to acknowledge. Anyway, that brings us to the end of part 19. I guess it's almost going to be end of season 1. And hope you're enjoying, hope you're still with me here. If you are, please leave a comment behind. I'm just hoping this series is not getting too long. But as you know, I really want to deal with this topic as if I'm taking a real class and not just for the heck of doing it, right? That is the reason why it's taking so much amount of time, so many videos. Hopefully, you're liking and enjoying it. So, the next set of videos will now move into a bigger monster, a bigger beast which we have to cage. And I guess all of you have almost guessed it. It's going to be WPA and WPA 2. So, I would say go ahead and get ready for another roller coaster ride. Next couple of videos are going to be even more interesting.